Welcome back everyone to 11.3, the integral test. To start us off, I want to remind us of a theorem we had back in chapter 7. So let's get to it.
So this theorem, back when we were doing improper integrals, says the improper integral of 1 to infinity of 1 over x to the p dx is convergent if p is greater than 1 and otherwise it's divergent. Now I want you to take a look at how close this is to the theorem that we're about to look at, this p-series test. So the p-series test says that the series from 1 to infinity of 1 over n to the p is convergent if p is greater than 1 and divergent otherwise. So we have to think, maybe these things are related, and certainly they are. In fact, we can prove the p-series test using this previous theorem back in our good old chapter 7 improper integrals here. And then we just apply the integral test, right? Because 1 over x to the p is going to be continuous, positive, and decreasing. So we have the three things that we need to apply the integral test. So this would be the proof, essentially, of why this theorem works. Now, this is a named theorem, p-series test. So I'm expecting that you will memorize this and be able to use it, right? This is part of our arsenal of theorems that we can apply to prove various series converge or diverge. So we will definitely be using this a little bit later. For the time though, let's try to do this example. We have the series from I equals 1 to infinity of 2 over 1 plus e to the I. And this doesn't exactly look like the p-series setup, so let's try to apply our integral test. So I'm going to go ahead and define a function, 2 over 1 plus e to the x. I'll use the x notation here now. And we should note that this is nice and continuous, right? E to the x is always positive, adding 1 to that stays positive, so there's no way we're dividing by 0 or taking a root of a negative number or something like this. So it's continuous, it's positive, right? So and that's again because e to the x is always greater than 0. Add 1 to that, it's still going to be greater than 0. 2 is greater than 0, so again, everything's kind of greater than 0 here. Dividing by two positives, you still get a positive. Okay, and then finally it is decreasing, and typically the way that we show decreasing, remember decreasing is in terms of a function, is that we show that its derivative is negative. Right? And especially now, this is a mildly complicated function, so let's take its derivative and show that it's negative on the interval from 1 to infinity. So okay, to take its derivative, maybe the first good step is to rewrite our function. Right? So instead of this 2 divided by 1 plus e to the x, right, this would require probably a quotient rule or something like that. So instead, let's go ahead and write it as 2 times 1 plus e to the x raised to the negative first power. Now we can just use the power rule, so we will get negative 2 times 1 plus e to the x raised to the negative second power, because of the power rule, times e to the x, because of course the chain rule. Okay, so now let's go ahead and rewrite this. Negative 2 times e to the x, and then when we raise something to the negative second power, that's the same thing as dividing by 1 plus e to the x squared. So now let's see, why would this be negative? Well, the denominator is always positive, e to the x is always positive, and negative 2 is always negative. So we have a negative times a positive divided by a positive, that's going to be negative. And therefore, because the derivative is negative, we know that the function itself is decreasing. All right, we've set it up. We can now apply the integral test. So let's go ahead and look at the integral from 1 to infinity of our function, 2 over 1 plus e to the x dx. And now the thing that we want to note here is that I'm going to try to use the comparison test on this integral. So the comparison test, right? Comparison test, we need our function, well, we should note our function is positive, and that our function right here is going to be smaller than 2 over e to the x. So if you just forget about this 1, you're going to get a larger function, right? Because we're dividing by less. Right? 1/3 is greater than 1/4, for instance. Okay, so now what about this function? If I integrate 2 times e to the negative x, which is the same thing as 2 over e to the x, well, again, I'm going to be using my definition of improper integrals. So this is the limit. I can pull out this 2 as we see here. And now let's go ahead and evaluate this limit. So this is going to be negative e to the negative x, evaluated from 1 to t. So if I plugged in t and I plugged in 1, well, I'd get, let me go ahead and rewrite this, right, with all these negative exponents. I could write this as 1 over e to the t minus 1 over e to the first power, right? So minus 1 over e to the first power, technically. Okay. All right. So as t gets very, very large, we have that this is going to be approaching 0, right? 1 over e to the t approaches 0. So therefore I have negative 2 times negative 1 over e, so that's just 2 over e. So we know that this thing converges. Well, because this thing converges and it is larger than my function, well, we know that by the comparison test that my original function, the integral from 1 to infinity of 2 over 1 plus e to the x dx, converges. And because this converges, we know then by the integral test, right? We've set this up so that the integral test is tied, right? These fates are tied. So we know that the series actually converges as well. So now we're comboing a few things here. Okay, and that is all there is to it. Oops, let me use a little bit thicker of a marker here, go a little bit faster. Okay, so with all this increasing and decreasing business, I thought it'd be nice to give you a nice bonus theorem here, really, of a faster way to tell, and most of the case would be faster anyway, of how to tell when something is increasing or decreasing. Just some quick tricks here. So that's what this next theorem is all about. So this is the math of increasing and decreasing positive continuous functions. So suppose that we have f1 and f2 are increasing functions, and g1 and g2 are decreasing functions on some interval I. Then, well, what happens when you add these things together, multiply, all that sort of stuff? Okay, so if we add two increasing functions together, as you would guess, it's probably increasing. What about if you multiply two increasing functions together? Again, probably increasing. Now, if you take the reciprocal, 1 over an increasing function, then it's probably decreasing, right? Now, what if you multiply an increasing function by a positive constant? Again, probably increasing. What if you multiply it by a negative constant, right? Negative c. Well, then it's probably decreasing. And we can play the exact same game again for decreasing functions. So if you add two decreasing functions together, decreasing. If you multiply two decreasing functions together, decreasing. If you take the reciprocal of a decreasing function, increasing. If you multiply a positive constant times a decreasing function, still decreasing. And if you multiply a negative constant times a decreasing function, increasing. So now I've left enough room that we'll prove one of these. It is a theorem. We can prove all of them if we wanted. But let's just go ahead and prove one of these. So this is, we're going to show that the product of two decreasing functions is decreasing. So the first thing I want to note is that g1 of x is greater than 0 and g2 of x is greater than 0. This is for all x in our interval. Why is this? Well, because it's positive and continuous function. So therefore, it's greater than 0. Now I also claim that the derivatives are negative, right? So the derivative of g1 at x is less than 0, and the derivative of g2 at x is less than 0. Why is this? Well, it's because they're decreasing functions, right? So decreasing means that their derivative is going to be negative. Okay, so now let's go ahead and observe that we want to show that their product is decreasing. So we want to show that the product has a negative derivative. So I'm going to try to take the derivative, and hopefully it'll be negative. And if it is, well, then I know it's decreasing. Okay, so let's just take the derivative. Well, product rule says I have the derivative of the first times the second plus the first times the derivative of the second. And our claim is that this thing, well, hopefully again, should be less than 0. So informally, we know that the derivative is negative and the function's positive. And so here, everywhere I see the function itself, g1 or g2, I plugged in positives. Everywhere I saw the derivative, I throw it in negatives. Positive times a negative is always negative, and if you add two negatives, it stays negative. All right, so this is informally what's going to happen here. Let's be a little bit more formal about this. So let me go ahead and erase this really quick. And now in words, again, this is a proof, so I want to be a little bit rigorous here. So because our function g1 is greater than 0, our function g2 is greater than 0, our function g1 prime, or the derivative, is less than 0, and g2 prime is less than 0, we know that these components, g1 prime of x times g2 of x, is less than 0, and g1 of x times g2 prime of x is less than 0. So therefore, their sum, g1 prime of x times g2 of x, plus g1 of x times g2 prime of x, is less than 0. This shows, of course, that the function itself, g1 of x times g2 of x, is decreasing, right? Because its derivative is less than 0. All right, so this is how the proof of one of these goes. You can imagine how the proof of the others would go. All right, let's move on. We have a couple more examples to wrap up this video, and that'll end 11.3 for us. Oh, I guess really quick before we move on, let's go back here and see if we applied this theorem of increasing decreasing to this function, how much easier it would be. So let me go ahead, I'll use green. All right, so what do we know? We know that 1 plus e to the x is an increasing function, right? And that's just because e to the x is increasing. So its reciprocal, 1 over 1 plus e to the x, is decreasing. And then if we multiply by a positive constant, aka 2 in this case, 2 over 1 plus e to the x is also decreasing. So I think this is a lot easier than taking the derivative and showing that it's negative. And while there are some cases where you will have to take the derivative, a lot of the time you can just apply this nice theorem. Okay, so let's move on. You have a nice example here. Determine if the following series are convergent or divergent. Now looking at this, well, if I pull out a -3, well, the series becomes a lot nicer. First of all the terms are now positive, so we can apply a lot of different types of theorems. But now also if I rewrite the square root, well, then I can see that this is k raised to the 3/2. And this is looking awfully p-series to me, right? So it's convergent if p is greater than 1. So in our case, let's go ahead and look. We had that this is k raised to the 3/2 power. Well, in this case, p is equal to 3/2, which that's certainly greater than 1. So therefore, by the p-series test, we know that our series is convergent. Well, let's just write the series from k equals 1 to infinity of 1 over k to the 3/2 is convergent. And then really we're using a different theorem that says that, well, when you multiply by a constant, this is also a convergent series. So when I multiply by -3, this is also convergent. Now it's important, this is good work right here. You need to always state, if you have a named theorem that you want to apply, you need to state that theorem. So by the p-series test, by the integral test, things like that. So, okay, let's do one more example here. We have a series from n equals 2 now to infinity of 5 over n times the natural log of n. So this one doesn't look p-series-ish to me. So let's go ahead and try to apply the integral test. So here's my function, 5 over x times natural log of x. And we'll note that this is continuous, but it wouldn't have been continuous at 1, right? Because the natural log of 1 is 0. So it's continuous on 2 to infinity. It's positive, right? And so this is because, well, of course, that 5 is greater than 0, x is greater than 0, right? It's 2 or bigger. And then the natural log is greater than 0. So natural log of x is greater than 0 on, again, 2 to infinity. Right, so it's on this specific interval. Okay, and then finally, I would like to show that this thing is decreasing. right? So why would this thing be decreasing? Why would our function be decreasing? Well, we know first of all that x is an increasing function. We also know that the natural log of x is an increasing function. So if you multiply two increasing functions together, it would stay increasing. Now how about if you take the reciprocal of that? Well, that's going to be decreasing. And then finally, if you multiply by a positive constant, stays decreasing. So our function 5 divided by x natural log x is decreasing. I think this is a lot easier than, taking the derivative. We'd have to use, a product rule, maybe even a quotient rule if we weren't being careful. So I think this is a lot easier. Okay, so we have this set up. We can now apply the integral test. We've shown that it satisfies the hypotheses. So if I take the improper integral, it's not going to be from 1 to infinity, but it's going to be 2 to infinity, right? Because our series starts at 2 now. So the improper integral 5 over x natural log x dx. So again, we know how to do improper integrals. It's going to have a limit in it. T goes to infinity of 2 to t of 1 over x natural log x dx. And we have to think, how do I integrate this thing? Okay, so let me use green really quick, and let's try to do just the indefinite integral. All right, so integrate 1 over x natural log x dx, and I'm going to use u substitution. So let's try u equals the natural log of x. So then du is 1 over x dx, and we can see we have that. So I can trade that part in for a du. So this is going to be 1 over u du, which is the natural log of the absolute value of u. And if I substituted back in for my u, this is going to be the natural log of the absolute value of the natural log of x. Whew. All right, so now I know how to integrate this thing. So this is going to be the limit as t goes to infinity of, now my integral is the natural log of the absolute value of the natural log of x from 2 to t. So when I plug in t, well, just everywhere I see an x, I'm now going to write a t. And then I'll plug in 2 and subtract this away. So minus the natural log of the absolute value of the natural log of 2. And now as t gets very, very large, right, the natural log of t is going to go towards infinity. And so that gets very large, and then the natural log of that heads towards infinity. So we essentially have infinity minus a constant. So that's going to be infinity, so it diverges. So by the integral test, we know, well, this improper integral diverged, so therefore this series must also diverge. So again, remember, this is good work right here. We're saying by the integral test. We're justifying our reasoning here.
Okay, and with that, I think we have a pretty good idea of how to apply the integral test. Go ahead and get started with your homework, and I'll see you next time in 11.4.